Hi. In the previous one, we fitted our first model and we were trying to interpret our results. Now, in this one, our task is to improve on top of that again, adding some more chunks, some novel chunks, if you will. And yeah, we got our model results summary and we were plotting it naively to check how different they are, how different the predictions are from the actual ones. And for instance, in here, we pretended as if it was a time series. Actually, I don't recommend checking a panel data such like this one using a line chart. What I would recommend would be the scatter plot, just like this one. And actually, maybe a better representation would be even using the predictions versus the real prices in a scatter plot, not the distance. So in here, if we say price and pred, again here price and pred, standing for predictions. This will give a scatter plot, just like the one below. And as you can see, this is not balanced. So this is another way of looking how bad the predictions are and how underfitting our model is. Okay. If this was a good model, imagine a diagonal line here, right? And that the dots would be scattered around that diagonal line, right? Because they wouldn't be much different than each other. This actually takes us to goodness of fit. Let's start a new markdown cell here. I am hitting the M here and it becomes a markdown cell. And then hit enter to write down whatever you want. So in here I will start a new title, goodness of fit. We are going to look into R-square more closely, and then maybe we should write R-square with this symbol. Yeah. We are going to check also the RMSE, how we implement an RMSE and R-squared by hand to practice a little and show how the underlying formulas work. Okay. Actually, we did a soft touch to R-squared, right? We got our first model summary here, and we claimed that our R-squared is 0.044%. R-squared, I think, is the most popular one in regression studies. Sometimes people ask if they should use R-squared or RMSE. Just stick to one. For myself, if my job is to explain the variation in the data and learn about that business domain, then I go for R-squared. And by checking different R-squared in the same data, I come up with different models, and I can see which one explains better the variation in my target variable. However, if my task is just to get my predictions, just like in a Kaggle prediction competition, I just go for RMSE, and smaller the better for RMSE, right? Because it's representing a metric for our errors. And R-square is always between 0 and 1. It's a ratio. Basically, R-squared, okay, in many different books and many different papers, they may have a different type of explanation for R-squared. The one that I really like is that it is showing the ratio of the explained variation in your target variable using your model, of course. So how much of the variation in your target variable is explained by your regression? That is R-squared. And we will compute it also by hand in a minute, and you will see what I mean more clearly. Okay, that's what R-squared is. Let's come here and try to formulate what I just said. So the R-squared should be the variation in your predictions divided to variation in your target variable. In this case, it is the price. So we can just straightforward. We can just say variation of what was this data frame's name? It is df2, right? Yeah, df2. So select your prediction column. This simply gives you the variation. It's a formula in NumPy, okay? And then do the same for the other column, that is df2. I think it was price, right? So if you print this, okay, there are lots of decimals. Let's just round this to 3 decimals for readability. Round, and I want just 3 decimals, maybe 2, but anyway, doesn't matter. See, this is exactly the same number that we were looking at over here in the model summary output. Where is it? It's here. So that's why it is important to know that it is just a ratio between the variations, and it is the explained variation, okay? But of course, I don't recommend doing it by hand. Just get the model summary and use it. How about RMSE? Well, when we fit an ordinary least squared model, it is already using the RMSE formula under the hood. It is the best. It is the best line, if you will, that minimizes the errors, right? And we can also say that it is the square root of sum of residual squared, something like that. It is saying that like that may be a bit confusing, but let's formulate it. Let's also compute RMSE by hand in our data. It is df2. By the way, I just want to print the head of df2. Just remember what it was. Okay, we have our price and predictions here. And we already have our residuals. We talked a little about residuals in the previous one. Here, I want to go ahead and implement RMSE by hand. And it's going to be, let me open my sketchpad also. Let's open a blank one from the beginning. Okay, I need a new one, like a graph paper. Okay, we talked about RMSE a little in the previous one. Now we are going to dive more into it. So it is root mean squared error, right? So there is our residuals, and how did we compute the residual? We just subtracted predictions minus the real price. That's how we did it. We need the summation of the entire data set. So we sum them up. So this symbol now stands for summing up. We sum up all the residuals to find the average. So we get the average. However, we get the average of the squared residuals. Okay, not simply the residuals, but we square them. Here you can remember this logic, like we are trying to get rid of the negatives, a kind of like that. Because if you check your residuals, there are lots of negatives, right? We want to get rid of them. We want to come up with a positive number, and because of that, we squared them, and then we average them. Remember, we are trying to come up with a representative single metric for representing our errors. That's our accuracy metric. Then we average them. That's it. However, this n is representing for the total number of samples. In this case, this is equals to the length of our data set. And now we squared them, so it means we expanded the number to a larger magnitude, right? The number just exploded to the square. Well, that's why comes the root mean, the square root. So we take the root and then we decrease the magnitude of the number back again to the same magnitude. That's why the RMSE will come with a to a scale similar to your target variable all the time. Okay. In this case, this RMSE will represent the price, actually the price error, if you will. So this is the formula, and we can implement this using our Pandas data frame. Let's go for it. So we are going to create. We don't need to create the residual. We already have the residual, right? We need to square it according to this formula. First, we need to square it. So I'm going to use the log method to create a new column. I will call it residual squared, like this. And then this is going to be the residual. Actually, we can do it in so many different ways, but this is how I'm going to do that. I'm going to apply a lambda function just to practice it. Why not? So what I'm doing here is I'm creating a function on the go. We call this a lambda function. It will iterate through each row and it will square the residuals, and then it will create a new column called residual squared, and we will see the result. Let's see if this works. Let's run this. Now if we check the head again, let's check. We have a new column, right? And it is the squared residual. But we need the average of it, right? We are trying to get a single metric. Let's get the average of it. Mean squared error, MSE. In the Scikit-Learn and other documentation, you will see it under this name, MSE, mean squared error. That's what it is. Again, I will use a function called mean from NumPy. And what I need is the average of that column that I created just now. It is the residual squared. Let's see what this gives us, if this function works. Yeah, okay. 8,000 is the mean squared error. Generally speaking, mean squared errors are huge numbers because we explode them, right, by taking the square and then we average it. And here comes the RMSE to the rescue. For interpretability, it is really better to take this square root. And np sqrt, if you hit tab, you will see your options, and then you are going to take the square root of MSE. Then you will see 89. So this is the error we are making on average, and you can see it like 89 euros or dollars error for each prediction and for all the predictions. And you can really see that here, right? In this representative scatter plot, you can see how different the predictions are from the prices. However, this is of course implementing by hand, and you actually shouldn't do that. You should use the Scikit-Learn formula for that. It is Scikit-Learn mean squared error. You should see it in the documentation. It's here. This is going to compute the mean squared error for you, and it is much more efficient to use inbuilt functions than implementing them by hand. Let's quickly copy this and use it. This will be a good unit test. We will see if it is going to compute the same number. We are going to import this from this module. And how to use this function? Let's quickly check the documentation. It has two mandatory parameters, the y_true and y_pred, naturally, because we are going to compare them, right? And there is another nice parameter here, squared. So if this is true, then it returns mean squared error, and if it is false, it requires RMSE. This is good. Actually, we can directly return root mean squared error by equalizing this squared to false, right? Great. Remember, the documentation is your best friend all the time. I don't recommend blindly Googling first. First go to the documentation, try to read a little, and then go to Stack Overflow and to the other sources. So in this case, our RMSE is going to be mean squared error. It expects y_true, right? y_true and y_pred. We know our y_true is df2 price. This is y_true. And then our y_pred is df2 pred, not df_pred, but df2 pred. And then there was this nice parameter called squared. I can also hit Shift tab and open the documentation also in Jupyter Notebook. Look, this is quite handy. If you hit Shift tab, you can already read what you need. And here it is, squared. By default, it is true. This is what it says. However, I want it to be false to return the RMSE. Let's see what it gives us. 89, the same number, and I'm happy. Cool. We now computed the R-squared and RMSE by hand, and also we used Scikit-Learn. Now we should go into multiple linear regression actually. Let's open a new title here. Multiple linear regression. Here we are hoping actually to add more explanatory variables, add more variables to the right hand variables, and explain more variation. This is what we hope, right? And we can, I think, also add some dummy variables here. Remember, in the previous one we talked about the usage of dummy variables in linear regressions. They can take two values, 0 and 1. The hotel can be either a close one to the city center or a further away one to the city center. So it is a binary variable, 0 and 1. We can, I think, add some dummy variables like this in the multiple linear regression to control for stars, for instance. If 3-star, 4-star, 3.5-star hotels can all be dummy variables, binary variables, if you will. And then we can add also the distance and the ratings of the hotels and come up with a better model maybe to explain more variation. Okay. Let's give a short break here, and then I will start a new one for the multiple linear regression. We are going to do some filtering, some data transformation. We will think about log price, the logarithm of the price, how it is distributed, etc., etc. And then we are going to fit another ordinary least squared or a linear regression model, or let's say multiple linear regression model. And we are going to interpret its coefficients again, how interpretation changes when you have a multiple regression, and are you able to get closer to causality, and how to do that actually? Okay, let's meet in the next one.
Hey everyone, thanks for watching. If you enjoyed this video, please let us know by liking and subscribing. If there's another topic that you'd like to learn more about, leave us a comment. We would love to hear from you. And if you want to become a coding pro, visit our website at codingnomads.co. See you next time.